Well, thank you, Dean Wallace, and just for organizing this whole series. And I know we have some great talks planned later on. I got to go first, not because this is the best one, but because of the date. The Fibonacci numbers start off 1, 1, 2, 3, and so November it's 11, but we can say it's a 1 and a 1, and then 2, 3, and then I guess we should have probably had it at like 5, 8 in the morning or something like that. But I don't know. I don't know how many people would actually come. So thank you all for coming out, though, and for being a part of this. So just some things here with mathematics and beauty. This is something that typically we might not think to put together, but it's something that is very much a part of what mathematicians have said. So we have a quote here by David Hume, and beauty exists merely in the mind which contemplates them. This is kind of like beauty is in the eye of the beholder, as some might say. But mathematicians over the years have been saying other things. So mathematics rightly viewed possesses not only truth, but supreme beauty. And the mathematicians' patterns, like the painters or the poets, must be beautiful. The ideas, like the colors of the words, must fit together in a harmonious way. And then Paul Dirac, who's more of a physicist but has done some mathematics as well, actually went as far as say it's more important to have beauty in one's equations rather than to have them fit at spearmint. And so we will see all of these kinds of things here playing out tonight. But first, just an overview of what we'll see. So Fibonacci numbers and the golden ratio. We will see some mathematical connections between these because this is a math talk. But then we'll also open it up and we'll see some other things as well. So some connections to a lot of other things, which is why we have some of these things sitting up here, which we'll get to. So Fibonacci numbers, what are these? Well, I kind of already mentioned this. You start off with 2 1s and you add them together. And you add them together to get what? 2. And then you add 1 plus 2 together and you get 3. And then 2 plus 3 and you get 5. And then 3 plus 5 and you get 8. And you kind of get the idea, right? You just keep adding the 2 previous numbers together and then you get the next one. So a very simple concept here, and you could keep going with this. We would define this here using a recursive sort of pattern, and you may have seen this before. Now, you may have seen it starting at 0. You could start it at 0 and 1 and put them together and have like a 0th term being 0, but it will give you the same list of numbers here. And you see here the overall pattern and how the first 2 are defined, and once we have those, we're off and running, and we recursively are able to define everything else from that. Now, this goes back not to Fibonacci originally, because as like many things in math, things get named after people who discover them 2nd or 3rd or 4th, and that's no different here with Fibonacci numbers. This actually goes back to ancient India, and there was a way to analyze poetry in Sanskrit. And so the idea is called prosody, but you can classify syllables into either long syllables or short syllables. And the rule is that 1 long syllable is equal to 2 short syllables. And so back in about 200 BC, an Indian mathematician named Pingala started to look at the idea of how many possible patterns could you have of a certain syllable length. And so we can just look here at some examples. So if you look here, again, L will represent 2 units for a long syllable, and S will represent 1 syllable for a short unit. So if you have a unit of 1, then the only way to do that is to just put an S, a short syllable. If you have a 2-unit pattern, well, you could put 2 shorts together, or you could put a single long together. And so notice there are two different patterns. Now, if you have 3 units, a 3-syllable pattern, you could put 3 shorts together. You could put a long and a short, or then you could do a short and a long. And notice now we have 3 patterns. For 4 units, what could we do? Well, you start to think about it. You could put 4 shorts together. You could put a long and 2 shorts, and you could move around where the long is in the overall pattern, or you could put 2 longs together. And notice we now have 5 patterns. And so some familiar things are starting to show up here in red, and those actually are the Fibonacci numbers. If we go 1 step further, we see it even more. So 5 units long, these are the possible ways of doing this, and we notice there are 8 ways to do it. Now, we would probably want to count these up a little bit better than what we just did in listing them off. If you notice, how could you get another syllable here, or another unit length? Well, you could think about taking and looking at a 5-unit length here. Well, take something with 4 units and add another short to the beginning. So that's one thing you could do. Or you could take something that was 3 units long and add another long syllable at the beginning of that. And that would also give you another set of patterns here. And so here are the overall patterns that we have of syllables, and they're arranged a little bit differently. And it shows us something here. It shows us that in general, for n syllables, what do we need to do? Well, we add a short syllable to the beginning of every n-1 pattern and a long syllable to the beginning of every n-2 pattern. So here is the overall recursive sequence showing up here in this idea of just counting syllable lengths in poetry. So that was initially where this Fibonacci sequence has been tracked back to, but then it was rediscovered by Fibonacci. And so Fibonacci here is also known as Leonardo of Pisa. That was his actual name, and then he was given the nickname Fibonacci later on in life. But he wrote a book called Liber Abaci. And this is remarkable, not just because this is where the Fibonacci sequence shows up in Western mathematics, but it's actually where we get our Hindu-Arabic numbers appearing in Western mathematics for the first time. So up until this point, people were using Roman numerals to do calculations, and again, that's very cumbersome to try to do. So he introduced Hindu-Arabic numerals, which was a good thing, and then also positional notation. The notion that if you have a number, the value of the number is determined by where it is positioned. And so this cuts down on the number of overall numerals that you have to have in a numeration system. And so it's a very good thing here. So in addition to this Fibonacci sequence, we get these very good things. And again, numeration systems are really a technological marvel whenever you think about it that just goes unnoticed, because when was the last time you tried to do a calculation in Roman numerals? Well, you didn't. The system works so well that we've adopted it, and we've done a lot with that. So, so anyway, there's a text. This is actually from a page from this the Liber Abaci, and I expanded one section. It's a little blurry, but you can see here that the Fibonacci numbers are showing up right here. Again, this is a 3, which looks a little different from how we would write a 3. That's a 5, which would look a little different from our 5, but here is 8. And then right down there is 13. So we get the Fibonacci numbers showing up. Now, why did they show up in here? Well, Fibonacci was interested in rabbits. And he was interested in, that's really why we have this right here. He was interested in looking at a colony of rabbits here under some idealized conditions. And again, he said, a certain man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that pair in a year, if it's supposed that every month each pair begets a new pair from which the second month on becomes productive? So summing this up, what he was saying was a few things that we would do in a mathematical modeling sort of situation. We make some assumptions and change the problem into something that's probably quite unrealistic in the real world. What he said was that rabbits here will take 1 month to mature, after which they can start to have baby rabbits. Each rabbit will produce a pair. The assumption is that there is a male and female pair so that they can continue to have rabbits, and that rabbits would never die. So we just keep counting up the rabbits. And so what we end up with, though, after 1 month, there's 1 pair. After 2 months, well, there's a new pair born, and now there are 2 pairs total. Month 3, so the original female produces a second pair, and so there are 3 pairs total. Again, the pair from the previous month that was born is not mature enough to produce any new rabbits yet. And then we keep going. After 4 months, what do we have? Well, the original females produce the 3rd pair. The female born 2 months ago has produced the 1st pair, and so now there are a total of 5 pairs. And again, we get the Fibonacci numbers showing up. We can see this a little bit better here by this chart, but the basic idea is we're counting up old rabbit pairs and then new rabbit pairs, and we see how we combine those together to get this Fibonacci sequence yet again. So after 1 year, how many are we going to have? Well, we have a lot, actually, 233 pairs. And Fibonacci didn't ask this, but how many would we have after 2 years? Well, this, again, because it's a recursive sequence and it keeps building, after 2 years, we have over 75,000 pairs of rabbits. Again, under these idealized situation, and again, quite impractical, really, in all honesty, but it did introduce this idea into Western mathematics. Here is the sequence, and you can just see how big the numbers get. There are a lot of interesting things about these numbers. One, a theorem by a mathematician named Cassini, who said if you take the product of 2 Fibonacci numbers that are apart from each other, then you take the one in the middle and you subtract it square, you're going to get plus or minus 1 out of that. And so just seeing right here in the Fibonacci numbers, if we use 3 and 5 here, or 3, 5, and 8, so what we're going to do is we're going to multiply these two together and then subtract 5 squared from it. And so we see that we get 24 minus 25, which will be -1. We then, if we do 5, 8, and 13, again, multiply 5 and 13 together, and then square 8, and we subtract, we get 65 minus 64, which is a positive 1. And so this is a nice pattern that we have in this Fibonacci sequence of numbers that, again, thinking of as counting poetry, syllables in poetry, counting rabbits, but yet there's some mathematical structure to it. Another theorem due to Kepler is if you add up all of the Fibonacci numbers up to a certain point, then what does this do? You then would skip a Fibonacci number and then subtract 1. So again, here's the Fibonacci numbers. If we add up 1 plus 2 plus 1 plus 1 plus 2, we get 4. Notice that is 5 minus 1. So we do 1, 1, 2, skip the 3, and then subtract 1 from that 5 right there. If we add up this, we would then get 7. Again, we are skipping over 8, or skipping over the 5 and getting 8, so 8 minus 1. And we could continue doing this. So if we wanted to add up a series of Fibonacci numbers, we could do this in a very, very easy way with this formula. So moving on from this then, the other topic mentioned tonight was the golden ratio. And this at first will seem like it might not have much to do with the Fibonacci numbers, but it turns out these are actually intimately connected quite well. So what is the golden ratio? Well, we move to the world of geometry here to define this. And the golden ratio, it starts off with saying that we have two numbers in this following relationship. The idea is we have a line segment. We take the line segment and we split it at some point. Now, what point do we split it at there? Well, we split it at the point so that the ratio of the whole line segment to the longer is the same thing as the longer line segment to the shorter piece. So that's what this is saying here. And so again, we could decide where to cut this, but it has to be that we fulfill these two ratios right here, and they have to be equal to one another. Now, we're being a little anachronistic here because we're calling this the golden ratio. Initially, it was not called that. And also, we're using this symbol right here. The symbol is called phi. And again, this is something that came much later in the history, but just to not clutter up the slides, that's what we'll refer to it as. Now, what would the value of this be? Well, we can figure that out. If you just take this and break this up, this fraction. So a divided by a would be 1, and then we have b over a. So notice we have 1 plus b over a. Now, a over b was equal to phi, so b over a would be its reciprocal. So notice we have a relationship here. Phi is equal to 1 plus 1 over phi. So how do we solve that for phi? Well, if we multiply through by phi, we now have a quadratic formula, and we can use our quadratic equation, and we get that phi is equal to 1 plus the square root of 5 divided by 2. So this is a number, and it is an irrational number. It cannot be expressed as a ratio of two whole numbers. And it's very important, actually, in some constructions in geometry, as we'll see. Again, this was first called an extreme and mean ratio by Euclid. Euclid was a geometer who wrote a famous textbook that was studied and has been studied by thousands of people across history. Lincoln used it to become a lawyer. Napoleon studied it while he was on the battlefield. And all sorts of people have studied from this textbook called the Elements. And so this was taking all of the known knowledge about geometry at the time and systematizing it in such a way that you start off with just a few postulates at the very beginning and a few definitions. And from those definitions and postulates, you can then talk about all sorts of theorems and develop, just using logic alone and mathematical proof, a whole system of geometry. And so that is what Euclid did. And so this is initially how this was defined. Again, this is just what we essentially just saw here, but these are, notice the ratio of the line segments here was how this was defined. So why do we need this? Well, to construct a regular pentagon, we need to have this golden ratio in order to do this. If you notice right here, here is this overall segment AB. We are cutting it right here in such a way that we are able to then put this line down here, and this will be used in the construction of a pentagon. What the Greeks would do in their geometry is they didn't have protractors to measure out angles. They would use a compass that could draw an arc, and they would use a straight edge, which was like a ruler, but there were no measurements or no lines to measure out an actual line segment. And so they would just be able to extend straight lines. They were able to draw arcs and circles, and that is how they would use, what they would use to construct geometrical figures. And so that's what they did here. And we see that with doing this process a little bit more, we have a lot of extreme and mean ratios being cut here. So just keeping with the overall formula, we have here's the big segment, here is the bigger of the two that we split it into. Notice that's showing up here and here and here and here. It's also showing up right here if we went from F to this intersection point. So we have a lot of these being used to further our ultimate goal of constructing that regular pentagon right there. And so this regular pentagon was important not just to make a pentagon, but to do something even more grander. The overall elements, the scope of the whole 13 books of the elements, goes to construction of the Platonic solids. Now, what are the Platonic solids here? Well, you can see them right here. These are convex, meaning that they don't dent inward or anything like that. They're three-dimensional, and you put them together by using the same regular polygons, meaning that the polygons would have the same angle measure and the same length measure. So there are 5 ways to do that, and that is it. So there are other ways you can put polygons together, but you have to use different sizes of polygons or different polygons altogether. So we see here a tetrahedron, which is like a pyramid. We have a cube, an octahedron, a dodecahedron, and then an icosahedron. So I brought in here our departmental, here's our dodecahedron, and then our icosahedron right here, and we actually have the sides numbered. So you see that there are 20 triangles that get put together to make this icosahedron, and there are 12 pentagons that get put together to make the dodecahedron. And so we could really spend a lot of time just looking at this slide. We won't, unfortunately, but you just notice there's some structure happening here and some interesting things. Notice the cube. There are 6 squares that form its faces, and there are 6 vertices in the octahedron. Likewise, there are 8 vertices here, and there are 8 equilateral triangles. It's not a mistake or anything like that. There's actually something called a dual structure to these polygons, in which you can collapse a face to a vertex and then expand out a vertex to a face in an interesting way. And notice that also the icosahedron, 20 triangles, 20 vertices in the dodecahedron, and then 12 vertices, 12 regular pentagons here. And so these two, icosahedron and dodecahedrons, are also related to one another. And so why do we need to construct the golden ratio? Well, to construct a regular pentagon. And why do we need to construct a regular pentagon? Well, to construct a dodecahedron and an icosahedron as well. And so that's why the Greeks cared about doing this, and why this was an important concept for them in mathematics. Now, why, even more beyond this, why was it important? Well, because really a whole system here of philosophy and their worldview in terms of the structure of the universe. So they had 4 elements. And the 4 elements, earth, fire, wind, and water, they then took these elements and matched them up with certain Platonic solids. Now, why did they do this? Well, because they said if you drop some earth on the ground, it is fairly stable and it will just fall flat, much like a cube would if you dropped it. Whereas if you have an icosahedron here, it kind of moves around and is quite fluid, much like water would be. And so they came up with this whole system of how things would work, and things were like hot and cold and wet and dry, and there was a certain combination of how all these things would come together. But you notice here, there are 4 elements, but there are 5 Platonic solids. So where's the 5th one? Well, it's the 5th element here, okay? So what is the 5th element? Well, this got a bit of a mystical flavor to it here from Plato. So this is from Timaeus. He said there was a 5th combination which God used in the delineation of the universe. And so this 5th element here, this was something that created being. It was looked upon as a kind of an ether that pervaded all of space in some cases, or it was actually the structure of the universe itself. So the universe itself sat inside an entire dodecahedron was a concept that came from this. And there's a lot of things we could trace in the history of physics and that kind of thing in terms of how the universe is structured that comes out of this. But it is quite interesting. So moving onward, though, a little bit. Luca Pacioli. So this, he's called the father of accounting because he took the Venetian system of a double booking system, and he actually wrote it down and introduced that to much of the rest of Europe, and so he is famous for that. He's also famous, though, for compiling a bunch of mathematics at the time. and writing it in a book. It was called the Summa. But he is also important in talking about the golden ratio. Now, if you look here, he is giving a lesson to someone who is unknown. He has a copy of Euclid right here, and he is doing one of the proofs here. And if you look on the table here, what do you see? Well, there's a dodecahedron sitting there. And so here he wrote a book also called The Divine Proportion. In the divine proportion here, you can see some more geometric shapes. You can see here another dodecahedron, and the other Platonic solids were reproduced here. What's interesting about this, though, is Leonardo da Vinci was the one who actually drew these pictures for this. He was a contemporary with Leonardo, and he knew him. And so Leonardo either constructed some wooden models and then drew the pictures from those, or he actually drew them just on his own without any models. Again, pretty good perspective. And we get to see kind of a three-dimensional representation of a dodecahedron. So in the chapter 5 of the Divine Proportion, Luca Pacioli has 5 reasons for why he calls the golden ratio the divine proportion. And this might be a little strange to us, but it was definitely not strange to him in connecting up things of faith with things of mathematics. And what did he say here? Well, the unique value of the golden ratio pointed to the unity of God, and then that there were 3 line segments in the definition. The big line segment and then the 2 smaller ones pointed to the Trinity. The fact that the overall ratio was irrational pointed to the incomprehensibility of God. The fact that this was a mathematical constant and it didn't matter the overall line segment length that you started with, that pointed to the invariability of God. And then the construction of the dodecahedron, well, this was necessary for that construction, much as God created being and imposed being into the world. And so he used this, again, and called it the divine proportion. And again, this is not really any mathematical reasons for doing this, though he used those to support his statements. Now, what this did, though, is this took the golden ratio and kind of elevated it to something different. And it created some more meaning for it. It's not just something that you use now to create pentagons and dodecahedrons. You need this to, it's something telling us about God, and it's telling us something about the universe itself. And so this then moved on. Kepler went with this, and he remarks here that geometry has 2 great treasures. One is the theorem of Pythagoras, the other division of a line into its stream and mean ratio. And so this is the golden ratio again, how they would refer to it. The first we may compare to a measure of gold, the second we may name as a precious jewel. And so he counted this, again, with quite high value because of how it worked in his overall system of the universe. Now, what you see here is a model from the Mysterium Cosmographicum of Kepler from 1596. And what do you see here? Well, this is a heliocentric model of the solar system. And notice that we have Platonic solids here. We have a cube right here, and then we have a tetrahedron in here. Going further in, well, here is our dodecahedron. We then have an icosahedron, and then in the middle here, we have an octahedron, and then there's a sun right in the middle. Now, what he did, at the time there were only 5 planets that were known, and so he used these actually between each of the planets' orbits. And he said because there are 5 Platonic solids, well, that's how the universe and the solar system has been created, and so put together the system of how this would all work. Now, he had certain reasons for why they went in certain places. Saturn was a lonely planet, and the cube seemed like the loneliest Platonic solid. Again, I don't know exactly why he said that, but that's what he said, and that's how he put this together. But notice where is Earth in this whole concept? Well, here's the dodecahedron, here's the icosahedron. Earth is actually between those 2. And what did we need? Well, we needed the divine ratio, or the golden ratio, to construct the icosahedron and the dodecahedron. And so we need that in some ways to create Earth in his system. Now, it turned out that this isn't actually how things work, but from this he did actually, the laws of planetary motion were developed from this and alongside of this, and that was good, and it stayed around, that planets move in ellipses rather than in circles and things of that nature. So, so moving on here though, just naming and notation, again, I said we're talking about things a little bit backwards in some ways. In 1835 here, the first known use of the term golden section here. So again, in German, goldener Schnitt. And then in the early 20th century, Mark-Bar introduced the notation of phi, standing for Phidias, who was a Greek sculptor, and it was said that he used the golden ratio in his sculptures. And so, again, this is fairly late in terms of the development that we're actually using phi and calling this a golden section or a golden ratio. Okay, so what is the decimal expansion of this? We talked about the fact that this is an irrational, and so we can take this and we would calculate this. This was done in the 1600s for the first time. And we get this nice decimal expansion. And again, this is not too interesting until we start to look at some identities here. And so this is the root. So if we divide both sides by phi, we get that phi is equal to 1 plus 1 over phi. And so this, in other words, that this 1 over phi is equal to phi minus 1. So looking here, the square of phi is just 1 more of phi, and the reciprocal of phi is 1 less than phi. So we notice that all these decimals are exactly the same. The only thing we're changing is the first thing right there, which is quite an interesting property for a number to have. It goes a little bit further than this, though. Again, if we were to start with this and then take the square root of it, what would happen? Well, we get phi is equal to 1 plus phi. But now we have taken phi and we've defined it in terms of a square root of an expression that involves itself. So we could basically nest this thing within itself over and over and over. So we do this again, and then we could keep doing this. So phi is this weird sort of infinite square root that we could set up. And we could see that if you stop it at any one point, it wouldn't quite be phi yet. But again, we're saying if you take a limit of this whole process, this would actually equal phi. Okay, what else could we do? Well, we could start with this, and we could look at dividing by phi. So notice that now phi is 1 plus its reciprocal. So do the same kind of process here again, and we have set this up, and we've defined this in terms of itself, and keep going. And we have what is called a continued fraction, an infinite continued fraction here. And so we don't, ones all the way down. We just keep putting ones and dividing over and over and over and over. So you could very easily with a pocket calculator calculate phi. Just take 1 and then add 1 to it and then take a reciprocal and add 1 to it, take a reciprocal, and just keep doing that over and over and over again. That's what this is showing. Okay, so mathematical connections. We have the Fibonacci sequence. We have the golden ratio. What in the world are these doing with each other, and why would we put them together in a talk here? Well, let's truncate this at successive points. So let's start here, and instead of doing this and saying take this forever, let's just stop it at certain points. So we would stop it here at 1. 1 is 1 over 1. 1 plus 1. So we would just say 1 plus 1, and we would leave all that out. Notice that's equal to 2. 1 plus 1 over 1 plus 1. So we would then take all of this away right here. And just keep this process going, and what do you notice? Well, 1 and 1, 2, 1, 3, 2, 5, 3, and so we now have the Fibonacci numbers showing up here in this. And we can keep going. So if we take ratios of successive Fibonacci numbers, they do a better and better job of approximating the golden ratio right here. And so this is, again, a connection between these things that is somewhat unexpected, but it is quite interesting here. Now, this is a theorem of Kepler. Kepler proved this, and the way to prove it is not too hard. Again, we know that, well, this is a math talk, so we do need to have some proofs here. Otherwise, it wouldn't be a math talk, right? But anyway, so we take this and we look and notice that this is recursively defined. And so we take the ratio of successive terms. So this is one term further than this. And again, rewriting this in terms of the sum of these two. And then this divided by that would be 1. What do we have here? Well, that is 1 less than this index right here. So in some ways, we have taken the reciprocal now of the ratio of 1 after it. It's now 1 before this one. So then we do something in calculus called a limit. So we just say take this limit. The limit this limit right here will not be any different than this limit right here. This is 1 more than this index. This right here is 1 more than this index. And so even though individually each of these fractions would be different from one another, when we take the limit, they will not be different from one another. And we just say set that limit equal to L. So what do we have here? Well, L, the limit of this term right here, is equal to 1 plus the reciprocal of L right here. So what do we have? Well, this is something familiar. Notice that this is L squared plus is equal to L plus 1, and so this is what's satisfied by the golden ratio. So we get the golden ratio spilling out of this with a very, very easy application of limits and quadratic formula again. Okay, so a question here. What's the 100th term of the sequence obtained by starting at 2 and then adding 2 for each successive term? So going with 2 and then 4 and then 6 and then 8. So what's the 100th term of that? No trick. 200, right? Okay. We just start. In general, we have 2 times n, and so the 100th term is 200. Okay, what's the 100th term of the Fibonacci sequence, though? Well, here, this is a little trickier, right? Because we could say, well, the 100th term is the 99th term plus the 98th term, but that doesn't really help us out too much, because we would need to know the 99th term and the 98th term, and the 98th term is the 97th plus the 96th, and we could keep this process going, but it's going to take a little while. You could go the other end, and you could just say, well, start with the first 2 terms, add them together, and then just keep going. So that would be the other thing. You could start building this up. But this is somewhat of an unsatisfactory answer, because if we want the 100th term or the 1000th term or the 1,000,000th term, it's going to take us a really long time to get there. So fortunately, there is a closed form for this. This is called de Moivre's formula, again, or Binets Formula. De Moivre also discovered it, and Euler also kind of probably knew about it as well, even though he doesn't get this attributed to him. But the nth Fibonacci number is given by this expression right here. And so notice we have some familiar things showing up here. What's that? Well, golden ratio. And this is the other root that we would have in the quadratic that we started with. And so we get these two. So the proof of this is a little trickier, but I did want you to see it. There's something called difference equations. And so from the theory of difference equations, we set this up and just notice that this is the recursion that we have for the Fibonacci sequence. From the theory of difference equations, the solution of this will be of this form. This is a constant, and then the r is a constant ratio to a power. So what do we have here? If we were to take this and plug this into this expression, we have a relationship between these 3 terms. We can factor out an n minus 2. And so now if we look at this, this is something that should look somewhat familiar to us. Both phi and then something called c, which is this other root, are solutions to this quadratic right here. And so we are able then to talk about the general form as this linear combination right here. So the initial conditions are then used to determine these 2 constants. So this is, again, a very, very straightforward application of this difference formula idea. Okay, so golden rectangles. Well, we can take side lengths here and that are in terms of the golden ratio and have something called a golden rectangle. And here we see this. We have in the math department, my wife put a quilt together basically that does some of this, and you may see that as you walk by. But notice here where we have these square areas of 1, 1, 2, 3, 5, 8, 13, 21, 34. So again, the Fibonacci numbers are all showing up in here. And we have them turning up, again, these are just in terms of the golden ratio is how we've set up all of these. So each of these rectangles are golden rectangles. This rectangle right here, and then this rectangle right here, and so on. We can then do something called a golden spiral. So we can connect up the edges of this, and we get a nice spiral here that has connections to some other things in terms of nature and in terms of the shape of a galaxy here, and the shape of a shell. All show up here in this. So the other idea that we have, we could take a circle and have something called a golden angle. So we take the sectors of a circle, and we set these up. And this ratio of this sector to this sector is the same idea as the golden ratio. We get this angle right here, which is about 137.8 or 0.08 degrees. And so this is an approximate value right here. But that gives us what's called the golden angle now. Okay, so further connections. Again, we've seen some mathematical connections, but what are some other things that we could see with this? Well, which is the fairest rectangle of them all? Okay, George Markowski did this experiment. It's sometimes said that golden rectangles are the most aesthetically pleasing rectangles. So take a look there. This is the audience participation part of the night. Take a look, figure out which rectangle is the best rectangle. What's the prettiest one? Take a look. Talk to your neighbor, try to. Okay, which one is it here? Well, there's actually 2. Those 2 right there. Anybody get them? Nobody? Nobody? Anybody get them? Okay, so again, this shows us something that what we have been told about the golden rectangle being maybe the most aesthetically pleasing might not necessarily be true. There's been all sorts of psychological tests dealing with this in which they have taken these, but a lot of them have been flawed in terms of how many rectangles do you have. If you only have like this line right here, you might be more inclined to pick it just out of random chance, and just the orientation as well. Very few people pick rectangles that are oriented this way. They typically pick rectangles oriented this way. So there's some interesting psychological things that we could see with this. Another psychological application of this was to take a model for human development in terms of the Fibonacci numbers. And so one is repeated because of the gestation being the first year. And then after that, we have years 1 through 5 denoting different stages of early childhood. And then 8 would be mid-child, 13 adolescent, 21 young adult, mid-adult, and then elder. We could probably even add them together even more and get 89 for the next Fibonacci number. And this sort of makes sense in some ways if you think about different stages of life, but there's nothing really mathematical about this. This is just something that somebody has put together that sounds good, but there's really not much to it. Okay, golden mean in architecture. So anybody ever hear that the Parthenon has a golden rectangle here, and several golden rectangles? Okay, so this is something that you will see repeated over and over, but there's really not much to it if you start to look at this a little more critically. When the Parthenon was constructed, the golden rectangle, and the golden ratio, though it was around, there's no record of this being used for any kind of ratios within this. You notice that these are golden rectangles that are put up here, but there's really no rhyme or reason. Notice this stretches beyond the rectangle. The steps below here actually stretch beyond it. This line does not actually line up with this pillar, and though you could look at some different ones, they're all somewhat flawed in that there is really no system to how we would evaluate this sort of thing. And so I thought we'd just take Rice Hall here, since it will be gone soon. And there's golden rectangles all over the place in Rice Hall, so I don't know if we should reconsider or not, but we probably shouldn't. So I don't think we would ever think that something like the golden rectangle would be associated to this building at all. But anyway, so why is this kind of flawed, and why can we do this, and why can we game it as easily as what I did right there? Well, just a question of error. If you have A and B within 1% of the actual measurement, then what happens whenever you take their ratio? How much is that ratio going to be? How much error is going to be associated to that? Well, you add the errors together. And so if you're looking at something like 1 divided by 1, you get 1. And then what if we change this and we make this a little bit larger and a little bit smaller, and you notice that we get about 2% difference right here. So this is very easy to game, and that's basically what I did whenever I did this. I just kind of played around with where exactly do you put the rectangle? Well, when you can put them whenever you want to, and you can make the width of the lines whatever you want them to be, it's very, very easy to do this kind of thing right here. Okay, okay. Now, it's not all bad though. This is an architect, Charles Edouard Generat, and he actually he wrote this. The sap of mathematics has flown through the veins of my work, both as an architect and painter. For music is always present with me. And in 1948, he put together a proportional system called the modular. And this is actually, he took the golden ratio and put it into his system. And so this is one instance in which we know that the golden ratio is being used because he actually said, I use the golden ratio to do this. Most of the time you don't get that. When you're just looking at the Parthenon or other buildings, you don't, unless you talk to the person who designed the building, you don't know. But he actually did this and put together a whole ergonomic system in terms of where would you put handles and levers and things like that. How do you design buildings? It's all different ratios, and these ratios are developed in terms of the golden ratios. And so, okay, full steam ahead. This is not just a STEM talk. We also have the arts here tonight. And so, so steam here. So looking here at the Mona Lisa, you've probably seen something like this as well. So and here we have golden rectangles all over the place, a golden spiral. Again, this is somewhat flawed because where do you put this? And how do you know where to place these things? Somebody else did this, and I looked on the internet, and there are a lot of different ways that people, and in other books, people have put these in different places. Again, Leonardo, though he knew Pacioli, so he knew about the divine proportion, he did not actually meet him until later on, and so he, there's no record where he has actually said, I'm using the golden ratio to put together my paintings and design them. So, anyway, so we see this right here, and then we also see things like this as well. You can take the Ratio Awakens here, and you can put together a golden spiral and rectangles here for the Darth Vader mask as well. So was that part of the design? Well, probably not, but you could definitely game this. So, all right. Now, Dali, well, this is a little different because here, again, Dali has not actually said that he used the golden ratio, but if we start to look at this, what do we see? Well, there's a dodecahedron here in the background. Theologically, I mean, there's a lot we could talk about with this that we won't be able to tonight, but if you look at the ratio of these sides as well, the canvas dimensions were reported to be this size, and so we see that we have something very close to the golden ratio here. Again, did he actually mean to use this? That could be up for grabs somewhat, but it is interesting that it's very close and that he took something like a dodecahedron and embedded that within, again, given it history with the golden ratio. Okay, music here. So whenever you came in, you may have heard some music playing. What was that all about? Well, there have been some studies that have shown that the Fibonacci sequence and golden ratio might have some ways that you could compose music. And so this Bartók's sonata for 2 pianos and percussion was playing earlier. And the idea is the semitones, as you go up here, are in certain intervals, and the intervals are all golden ratio intervals, as we have right here. Okay, Debussy here, in Le Maire, there are possibilities that the golden ratio and the Fibonacci numbers were used in that. And also, this was a book by Howitt, who's a musicologist. And again, it's not just that you look at the music and you say, well, the golden ratio is probably being used. There was a letter in which Debussy is writing to his publisher, and he says that there is a measure that was left out, and it's very important as regards number, the divine number. And so this is, again, the only indication that we have that he would have done something like this in his composition, but it is somewhat circumstantial, but it is somewhat interesting that would be, he would refer to the divine number in terms of the number of measures that he would have and all that. So there's been a whole study really in looking at his music and saying, well, at this climax you have it's the exact golden ratio point of the whole composition and things like that. Okay, Fibonacci retracement. So this is a concept from finance and investing. And so the idea is you can take Fibonacci numbers and look at their ratios. That will show you where stock prices and things like that change. And so here is here's an example of this. And the horizontal lines here are ratios of Fibonacci numbers here. And we see possibly something going on here. Again, there's nothing necessarily mathematical about this. This is an observation that people have made in studying these various things with stock prices and commodities trading and things like that. Okay, honeybee pedigree. Well, something entirely different here. Honeybees reproduce in that if you are a male honeybee, you only have a mom in terms of how things work. And so what does that mean? Well, a male bee has one parent, his mom. How many grandparents does the bee have? Well, 2, his mom's parents. And then how many great-grandparents? Well, his grandma has 2 parents, and then his grandpa has 1. And so we start to see the Fibonacci numbers show up here again in terms of the generations of a honeybee. Okay, and also too, I didn't get it up here, but the overall ratio of males to females in a colony is roughly or I guess females to males would be roughly the golden ratio as well in terms of how they propagate. So all sorts of other areas of botany. So this is why the pineapple's here. You may be wondering, well, what's the pineapple doing up there with everything else? So what happens here? Well, here's an idealized pineapple, and if you look and start to count the spirals, the Fibonacci numbers start to show up in the number of spirals that you have. Now, you could look at some more steep spirals, and they are different Fibonacci numbers typically whenever you start counting these up. In the seed arrangements of a sunflower, this again is an idealized picture of this, but you start to count the spirals here, and there are 21 spirals if you count them this way. If you count spirals that way, you see 34, 34 being another Fibonacci number. And then here we have 55, so we have another Fibonacci number showing up in the seed arrangement. So again, they don't always do this, so this is not some kind of biological law that will always happen. There are certain things in terms of stress and other environmental concerns that will change this kind of picture. This is somewhat idealized here. Okay, so just concluding thoughts here. The mathematical sciences particularly exhibit order, symmetry, and limitation, and these are the greatest forms of the beautiful. This is a quote by Aristotle, and so hopefully you have seen just some ways tonight that you can take these ideas from math and other areas and put them together and have something that truly is beautiful and amazing in God's creation and just how He's connected all of this together. And so thank you for coming. Here is further reading. If you are curious about some things, I'd be happy to talk to you.
Well, let's thank Dr. Taylor once again.